Hello, everyone. Thank you for being here. So today I'm going to talk to you about AI Epilepsy, a project we're currently developing at la Universidad de los Andes in Bogotá, in collaboration with Fundación Hospital Pediátrico La Misericordia, also known as OMI, and Biotecnología y Genética SAS, all with funding from the Colombian Ministry of Science. So, as a brief introduction, epilepsy is a neurological disorder characterized by an excessive and synchronic signaling between neurons, which leads to an increase in brain electrical activity and causes what we all know as seizures, with symptoms like loss of awareness and disturbance in movements. It can affect people of any age, and it's estimated that 50 million people worldwide suffer from this condition, and that each year there are 5 million new cases. So as of today, there are different sources of data and information for epilepsy diagnosis. We have patients' medical records. We also have neuropsychological tests that evaluate patients' motricity and cognition. And we have some other more complex exams like electroencephalography or EEG that seeks to measure electric activity in different regions of the brain. We also have images like MRIs that show brain structure and its integrity. And we also have peripheral blood microRNA sequencing that is like a new option being researched right now to find potential biomarkers for epilepsy. The first line of treatment for epilepsy is the prescription of anti-epileptic drugs. These are long-term therapies, at least 6 months for each therapy, and the main goal is to reduce the occurrence of seizures. Unfortunately, 30% of patients doesn't have a positive response to this treatment, and they have to undergo at least 2 drug regimes in order to be classified as patients with refractory or drug-resistant epilepsy. After this diagnosis, the next step is to identify the epileptogenic node and a later extraction through surgery. So with our team, we went to OMI and conduct different process of observation and different interviews in order to find improvement opportunities in the epilepsy diagnosis process. And we found that EEG and MRIs data analysis are complex and require a large amount of time and medical training. That there are no diagnostic tools that integrate all types of data, and that early diagnosis of refractoriness improves quality of life and prognostics for patients. Our proposed solution is AI Epilepsy. It's a user-friendly web application implementing machine learning and deep learning models, and it's meant to be used in pediatric patients in a clinical context. So what are some of the features that are right now in the latest version of AI Epilepsy? We have a platform where we can see a patient information summary. We also can associate diagnostic files like MRIs and EEGs to each patient and perform analysis on this data asynchronously. We achieve this by implementing this software architecture where we have 5 components. First, we have a monolithic application with front-end and back-end that is connected to 2 different data servers, one for structured data, where we can store results from analysis, and another for unstructured data, where are the files from MRIs and EEGs and sequencing information. We also have what we call a machine learning component, where are all the machine learning models and scripts, and it is connected through a messaging queue to the monolithic application, which allows users to run consults and queries while analyses are being done. And finally, there is a final connection to hospital servers to gather patients' information. We also integrated an MRI viewer from the people of EPAM. It has really interesting tools like area, distance, angle measuring, and even 3D reconstruction, which are all very useful in order to surgery planning. Another feature is an EEG seizure detection model. It has as an input the raw data from EEGs in EDF format. It is preprocessed and divided in 5-second windows, and the output will be for each window if it has seizure or if it is seizure-free. So how we train this model? First, we use these 3 public databases, really heterogeneous databases from different sources that are up to 500 hours of EEG scans, and all of them are annotated specifically for seizures. So to unify all this data, we follow this preprocessing workflow. We first ensure that all the files were in a bipolar configuration, then also that all files were in the same sampling rate. So we did subsampling to 56 hertz. The next step was filtering in order to filter possible noise caused by movement and other or blinking and artifacts in the files. So we apply a high pass filter of 0.5 hertz, a low pass of 70 hertz, and a notch filter of 50 hertz and 70 hertz depending on the source, or 70 hertz depending on the source of the file. The next step was normalization, and finally we divided all the files in 5-second fragments, and later again divided into different classes that were seizure and no seizure or seizure-free, according to the notation. And at the end we had 9,522 elements for each class. With this data set, we followed this experimental design for model training. So 90% of the data set was used in the training phase, and there we have two different approaches. First, we have a machine learning approach where we calculated 8 different feature subsets associated to signal properties, and also used the combination of all the 8 subsets. And this was the input to 5 classic machine learning algorithms that were random forest, support vector machine, k-nearest networks, decision tree classifier, and naive Bayes. And on the other hand, we have a deep learning approach where we train 6 different neural networks with different characteristics and layers like convolutional layers and also autoencoders and some recurrent layers. And at the end, we test these models with the other 10% of the data, and our metric of decision was F-score and our ROC. These are some of the results we obtained from these experiments. As we can see, most of the models had good performance, but the best ones were a convolutional neural network with an F-score of 0.923 and an ROC of 0.978. And the other one was a combination of a random forest model trained with the concatenation of all features that had a performance of 0.918 for its score and 0.975 for our ROC. So we took our best models trained with public data and dual testing with OMI data, data from the hospital. In this case, we tested a single file from a patient of 5 hours of duration. And these were the results. As we can see, there was like a big decrease in performance, where the best model had an F-score of 0.7 and a ROC of 0.656. So we delved deeper into these results. So the circular plot, where we can see the 5-second windows chronological placed all around the circle, and each of the tracks represents the model being trained. The black one would be the annotation, and each line represents a 5-second window that has seizure, or that has the label of seizure. As we can see, in some regions there is good performance. As we can see, for example, in the blue frame and the red frame, the detection is consistent with the annotation, like in these cases, and also here. But then there are some regions in which we have a lot of false positives, like here, and that's the reason why the performance is decreasing. This is a preliminary result. It's just one file from OMI. We are gathering more data in order to have like more strong conclusions and maybe hypotheses and possible solutions to this problem. Another feature in AI epilepsy is lesion localization for MRIs, specifically for cortical dysplasia type 2. In this case, we have 3 different machine learning models that each one is for each anatomical plane. They were trained by an undergrad student of our group called Nestor Gonzalez. The input to these models are the decon flare MRIs. The analysis is run individually for each image, and the output will be 3 labels. It will be the lesion is in the right hemisphere, the left hemisphere, or there is no lesion. This is how the model works. So we have our flare MRI, then we perform a feature calculation and a structural feature called histogram of oriented gradients. With this information, we do principal component analysis and choose the first 25 components as input to our support vector machine model. And at the end, we have our classification in these three labels. The results for these models were this. They have good performance. For the sagittal plane, we have 94.7 of accuracy. For coronal, 91.5. And for the transverse plane, we have 84.7. Now, for the microRNA sequencing data, we at the moment are independently running the pipeline from NF-core small RNA sequencing to build the microRNA expression profile, specifically the results from MIRDIP2 software. This expression profile is the input to AI epilepsy, where we have a database of potential microRNA biomarkers found in literature. And at the end, the output would be if these potential biomarkers are present in this expression profile. As future work, we plan to integrate an EEG viewer. Also, we want to train state-of-the-art brain anomaly detection models for MRIs. Also, models integrating all types of data for refractory epilepsy early diagnosis. And finally, we want to test our software with potential final users. Thank you.
Time for questions.
I'm sure you have done it, but I'm curious, like on the first results that you are showing, it actually looks like you are overfitting your model, because when you try the other patient, the benchmarking that you are using decreased a lot. Have you looked into
yes,
it?
it could be.
How did you do it?
Well, it could be possible that probably our models trained with public data are just like overfitting to this specifically data. We're going, right now, like this is like really preliminary result. It's just one file from just one patient, so we all at the moment don't know if it's maybe overfitting or it's because this specific patient probably has or is underrepresented on the public databases in terms of his age or seizure types or something like that. So we're gathering more data in order to test them and have like a more rigorous conclusion about.
So you are not using a testing.
Yes. Wait. So first, here we have 90% for training, and we do testing on 10% that is not used for the training. So in that case, well, this data that the model haven't seen. So probably that also says that there is no overfitting, but also probably, well, the model is too specific to the data we use in these three databases and not some external data. So
Congratulations.
thank you.